Hello friends, welcome back to the tetrahedron chemistry classes. So guys, today I am going to start lecture number 4 on IR spectroscopy. So today I am going to discuss the anharmonic oscillator model, and for this you need to know the Morse potential. But before going into the details of the fourth lecture, let us recapitulate what we have done so far in the lecture number 3. And moreover, in the description box you can find the links of the earlier 3 lectures on the IR spectroscopy. If you are a new viewer here and you want to start to learn your IR spectroscopy right from the beginning, so for you all the links of the first 3 lectures are given in the description box. You can go there. And for the viewers who are already actually the member of the tetrahedron chemistry classes family and followed this IR lecture, then you know in the last lecture what I have explained. In the last lecture I have explained the Hooke's law and the applications of the Hooke's law. Okay, so this was my last lecture, if you can recollect, right? Hooke's law and the applications. I have derived the Hooke's law and given the various forms of the Hooke's law, and then I have solved the various problems. See, this was the problem number 1, this was the problem number 2, this was my problem number 3, right? I have done lots of problem based on this. So today I am going to move further and I am going to discuss the anharmonic oscillator. But before going into the details of the anharmonic oscillator model, we actually need to think why actually we need the anharmonic oscillator. Okay, need for anharmonic oscillator. So I can write here. So guys, the answer is quite simple, though I have also actually thrown a little bit of light in my second lecture that we will, if in near future we will need the anharmonic oscillator, because harmonicity actually does not always there in the real molecules. Okay, so first of all you need to think in that particular manner. See, if I go back, right, what I can do, I can, so guys, this was the slide, right? This was the basically your bond length which I have plotted against the energy, and this was the actually harmonic oscillator. This is the parabola, you know. I have explained all these things in my earlier lecture, and here you can see the energy gap between all the vibrational levels are same. Okay, and this was actually nu bar or h nu, which was the Bohr's condition, right? But you know, this harmony which is actually I have shown in this particular slide does not actually follows in case of the real molecules. What actually this graph is explaining, okay, the potential energy function of the harmonic oscillator is suggesting that if the stretching of the bond, like you see here there is a little bit of stretching, here the stretching is little bit more, here I have stretched this thing more, right? And if I keep on doing this, so I am stretching my bond, see my bond very to the very large extent. Okay, if the stretching of the bond is increased indefinitely, according to this particular graph, potential energy will also going to increase indefinitely. But we know at the large internuclear distances, if the stretching is too much high, the true potential energy actually represents the bond dissociation energy. That means you cannot have any value of the you cannot have any value of the energy, right, which is actually corresponding to the stretching, because at higher energy, at higher, if you stretch the bond too large, then it will break. So this parabola generally does not follow at all for the real molecules. So that's why actually we need the Morse potential, or see, not Morse potential but the anharmonic oscillator model. Okay, so right, so this was the this was the need actually for the anharmonic oscillator. Okay, now what you can see, the concept of actually basically, if you can summarize, if you want to summarize this, the concept of the harmonic oscillator is actually for the perfectly elastic spring, and it is also it is valid for the perfectly elastic spring, and it is also valid for the real molecules if the stretching or the compression of the bond is very small, roughly say 5 to 10%. Okay, if your stretching or your compression is somewhere around 5 to 10%, then harmonic oscillator is very good. and holds very well. Okay, but we cannot stretch or compress the bond beyond this limitation, right? 5 to 10%. Okay, so what we can do, we need some other parameter which actually explains the stretching, which is stretching or compression, which is larger than the 10%. Okay, for this actually PM Morse, so you should remember the name of this gentleman. So to explain this, PM Morse basically what he did actually, he derived an equation, an energy equation, which generally we know as, he actually gives the Morse function basically, and he gave the equation just like that. E, right? The E is nothing but it is the Morse potential energy. E is the Morse potential energy, that is equals to D of EQ. DEQ is basically dissociation energy. Okay, and then 1 minus EXP. This is the exponential form, right? Instead of EXP you can write the E also, and then A REQ minus R, then you can close your bracket, and finally make the square of it. Okay, this is basically your Morse equation, and this energy is the Morse potential energy, right? And this DEQ is the dissociation energy of the bond. E is the exponential form. Okay, that means e to the power something, right? And A is the constant. This A is basically the constant, and basically this constant depends on the bond strength, right? So this equation is very, very important. Okay, now what we can do actually, for real molecules basically we need the harmonicity, and after that what we'll do, see if this equation, right, this Morse equation, this Morse potential equation, if this equation is used in the Schrödinger wave equation, then the pattern of the allowed vibrational levels, vibration energy level is found to be like that only, right? So what we will do actually, we'll write the Schrödinger wave equation, and in the Schrödinger wave equation we'll put this equation, right, which is the new equation where we have this particular A constant, right, and then we will have the new actually vibrational energy formula, which also includes the Anharmonicity parameter, right? And what would be those actually energy levels? So EV, vibrational energy, equals to V plus half of H nu, right, minus XE, V plus half square of it H nu, and this would be in the joules. So how actually I am getting this particular equation of energy, vibrational energy levels? Simply I actually put the Morse equation, Morse potential equation to the Schrödinger wave equation, and after the rigorous mathematics I'll get this result. So you not need to worry about how actually we can derive this particular equation. This actually we learn in the quantum mechanical treatment of the spectroscopy, and it is not important for the MSc students, and even for the CSIR net or the GATE examinations. It's too complicated, so we can safely avoid those mathematics, because this video is also for the biology students. I am not going into the details of that rigorous mathematics. Okay, so what I can see, this is the equation, right? This is the equation, but you know, in the IR spectrometry we seldom deal with the joules, we deal with the centimeter inverse, right, wave number. So we can convert this equation into the wave number. Okay, so here I can write in joules, energy in joules, and after that what we can do, we need energy in centimeter inverse. So as I already told you in my previous classes how we can convert this, we can divide this vibrational energy with the hc, where h is the Planck's constant, c is the speed of the light, and then you will have v plus half from the above equation. Okay, and h nu is there, then again I will divide this with hc, right, in both sides of the equation, minus xe v plus half square of it, h nu over hc, and this would be in the centimeter inverse. How? This h would cancel out, this h would cancel out, and you know nu by c is nothing but it is nu bar, which is the wave number. So this equation, right, this I can write as epsilon v. We can write it as epsilon v, and you should understand, the viewers should understand this thing. This epsilon v is basically what? Vibration energy divided by the Planck's constant and speed of the light. This you should know. This is something very, very important. There is difference between the E and the epsilon. Whenever you write the epsilon, it clearly indicates that you have divided your energy with the Planck's constant and the speed of the light. Okay, and this will give you the equation like that: EV equals to V plus half nu bar, okay, minus of XE V plus half of the square and the nu bar in the centimeter inverse. Okay, this equation is very, very important for you, right? Why this equation is very, very important? Because it is very, very helpful for the molecules which have the stretching or the compression of the bond, stretching or the compression of the bond larger than the 10%. Okay, what I forgot to tell about something, this XE, right? This XE is very, very important, which is anharmonicity constant. So I can write anharmonicity constant, anharmonicity constant, and this anharmonicity constant actually is having very, very low value, 0.01, right? The value of this anharmonicity constant is very, very low. You should remember this particular point, and the value of this anharmonicity constant is 0.01, roughly 0.01, not exactly, but roughly 0.01. I hope actually you understood this thing clearly. Okay, and if you want to calculate this anharmonicity constant, then you can calculate the anharmonicity constant by using this formula: anharmonicity constant XE equals to nu bar over 4 of dE, where dE is the dissociation energy, right? So in the competitive examination you may have the question based on this particular equation also, and later in this series I will try to solve the various problems based on the different formulas, and those lectures actually may include this formula also. I hope this is very, very clear to you. Now if this is very, very clear to you, what we can do, we can move further. Okay. So here in this particular slide you can see what I have written over there. Anharmonicity affects the molecular vibration in two ways. What are those two ways, right? So to explain all these things, I have to actually draw. Right, guys, so what you can see here, what I have written over there in the slide: anharmonicity affects the molecular vibration in the two ways. So to explain this effect of the anharmonicity on the molecular vibration, we need to understand this potential energy function of an anharmonic oscillator. So this is the potential energy function of an anharmonic oscillator. Here you can see the lines which I have drawn with the green dotted line. This is basically your Hooke's law, right? Harmonicity is there in this particular region. Okay, and this is the parabolic form, and this follows the Hooke's law, right? But it is valid only for the for the molecules where the stretching or the compression is less than 10%. But when you have the stretching and the compression actually more than 10%, then you need actually the Morse potential. And if you want to understand the effects of the anharmonicity, then you need to understand this. So how it is affecting. So before going into the explanation of this particular plot, you need to understand what is happening here. Here you see these are the vibration energy levels, right? V equals to 0, 1, 2, 3, 4, 5, 6, 7, and so on. and this actually is the continuum which we will obtain, and you can clearly see the difference here. If you focus here, you see this distance and this distance, they are same. Okay, this is also same, but as you go up, right, then the distance between the vibrational energy levels decreases. That means energy gap is slightly lower than the h nu or the nu bar. Here you see, in that case energy gap is what? Nu bar, and in that case also nu bar. But if you see here, then this energy gap would be less than your nu bar. This should be very, very important to understand. This is not h equals to h nu. So what is happening here in that case, right? Due to the anharmonicity, the vibrational energy levels, right, of the simple harmonic motion, which I have drawn here actually, are slightly lowered. This is very, very important, right? Less than h nu, which I have explained, and the spacing between them goes on steadily decreasing with increase in the vibrational quantum number. This you should know, right? And this would be very, very helpful when we calculate the energy required for the overtones, first overtone, second overtone, and so on, right? This would be very, very helpful there. And this DO is basically your dissociation energy, right? This DO is the dissociation energy, and it is experimentally determined dissociation energy. And DEQ is the dissociation energy of the molecule reckoned from the lowest vibrational quantum number, or the lowest point of the curve, right? So this is the bond dissociation energy, and this is the actual bond dissociation energy which we find experimentally, and this is actually the Morse potential. This value actually, which this is actually the Morse function, right? This, just like that, this graph is the for the anharmonic oscillator, right? And this for harmonic oscillator. You need to understand this. Or if you want to calculate the DO, so DO can vary, DE, not DO actually, DE. You can very easily calculate this by using this formula, DO plus h nu by 2, right? So we'll solve the numericals based on these also. So keeping in mind this Morse potential, Morse function, anharmonicity constant, and the equation, right? This particular equation will try to give you the number of the transitions possibles in the vibrational spectroscopy, right? And when you consider this anharmonicity, then the selection rule changes. Okay, earlier you can see, you have seen actually, right? Earlier you have seen in the vibrational spectroscopy, del V equals to plus minus 1 was the selection rule, one for emission, one for the absorption, and we are always interested in the absorption spectra. So in our case, only plus 1 is useful. Okay, this was the case of the Hooke's law, right? But when your Hooke's law is not valid actually, and you also takes account of your anharmonicity, right, then this vibrational this actually selection rule will not hold. Now you will have the new selection rule. So what would be the new selection rule? New selection rule would be plus minus 2, or even plus minus 3, etc. You may have this value, these values actually. Okay, and how many transitions actually are possible? So here I can show you. This is my lowest vibrational energy level, where I am having vibrational quantum number value 0, and here in the second I am having the vibrational quantum number of 1, and if you go up, then you may have the vibrational quantum number 2, and say this is where vibrational quantum number 3, V equals to 3. This is something very, very important, because I am going to explain the transitions in IR spectroscopy. Okay, this this is very easy to understand. When your molecules are changing their vibrational level from 0 to 1, it is nothing but it is fundamental vibration. So V0 to V1, is basically fundamental vibration. Fundamental vibrations I can write for this one. Okay, and these fundamental vibrations are always observed at room temperature. That means when you are doing your experiment or you are recording your spectra at the room temperature, then you will always find the fundamental band. And for this rule, you know, del V equals to plus minus 1, as I have explained. Okay, and then what in the next instance, what can happen actually? So this I can write here as F, where F represents the fundamental vibration, right? This is my way of explaining. You can make your own notes by understanding the things from here only. But sometimes in that, see, you know, in that case, here del V equals to plus minus 2. That means you may have this transition also from 0 to 2. So here in that case, del V equals to plus 2. When this happens, that means your molecules are promoted from the zero vibrational state to the second vibrational excited state. That means second vibrational energy levels, right? So in that case, you will get the first overtone. This will give you the first overtone. First overtone. Okay, and so I can write FO. FO means first overtone. Okay, and in that case, it may also happen that this may go from here to here. Okay, that means del V equals to plus 3. Okay, and when this happens, you will get your second overtone. You will get your second overtone. Similarly, you may have the third overtone, fourth overtone, right? But there is not much of importance of these actually overtones, right? Is higher order of overtones, right? And what happens next? See, if you increase the temperature, right, at higher temperatures, I can write at higher temperature. So when you increase the temperature, right, of the system, what will happen? Your molecules may actually promote from zero vibrational state to the first vibrational state. That means now your V1 would be greatly populated. See, earlier one, when you are at the room temperature, the maximum population of the molecules are in only V equals to 0. That means lowest vibrational state. But if you increase the temperature of the system, then your molecules may promote to the first vibrational level. Now this first vibrational level will have the appreciable population. That means now the transition would occur from V equals to 1. Right? So what can happen in that case? Here you may have this promotion. Right? When, see, this was your point 1, this was 2, this was 3. Now you may have the fourth point, right? Fourth, what you are doing in that case? Say here you see del V equals to 1. There is no problem in that. But here V is actually changing from V1 to V2, and since this is happening at the higher temperature, so this vibration is basically the hot band. This band is the hot band. As the name suggests, it is happening at the higher temperature. That's why it's the hot band. So this is first hot band. Okay, this is the first hot band. But if you increase the temperature further, and if you supply the energy further to the molecules, what may happen actually? Your molecules may promote from V equal to 0 to V equals to 2. So now at even higher temperature, you may have the appreciable populations of the molecules from the V equals to 2. That means now the transition would happen from V equals to V equals to 2 to V equals to 3. So this is, if this is your first hot band, okay, then above one is your second hot band, right? These things actually, guys, you need to understand. And this diagram, what I can write for this here, quantized energy levels. Okay, you can write like that. So I hope you understood the things completely. But please remember, there are certain things which you need to understand, right? See, these overtones, see, these fundamental vibrations are actually quite strong. Their intensity is very, very high. Okay, but for the overtones, right, when the vibrational quantum number is changing from changing by like +2, +3 and +4, these overtones, the intensity of these overtones is very very low compared to the fundamental vibration. It is always valid, right? And when this happens, actually this is the validation of the harmonic approximation. Okay, harmonic approximation means the overtones, right, which we are getting, the hot bands which we are getting, that means this first is this overtone, right, second this overtone, right. So these actually are basically harmonically forbidden. When they are harmonically forbidden, they are not allowed, their intensity is quite low. This thing you need to understand, and it is very very important. So and what about the hot bands? Actually I already told you, that means if you increase the temperature, then your population increases in the other vibrational levels. This is something very very important, and very easily by using your Boltzmann distribution law, right? When you use the Boltzmann distribution law, you can very easily calculate the population ratio also. Okay, so how, see, let us look one thing actually here. What is Boltzmann distribution law? That is N1 over N0 equals to e to the power of negative h nu 1 over kt. Right, this is the general expression, right? And you know nu bar is what? Nu by c. This you should know, right? And see, you know this thing. So that means the nu can be nu bar multiplied by c, right? And when you do this, right, say this is the equation number 1, this is the equation number 2, from 1 and 2, what we get actually? N1 over N0 equals to e to the power of negative h nu bar c. So what I can do, I can remove 1 from here. Mistakenly I have written this, okay? Divided by kt, okay? And when you solve this equation, basically, right, if you solve this is E negative, you can write the value of the Planck's constant here, which is 6.63 into 10 raised to the power minus 34, right? And you know the unit of this, meter square kilogram second inverse, right? See, why I am actually why I am spending too much of time in solving such kind of the problem. See, because if you are the biology student and don't know much of the mathematics, then it is always a very very hectic or the big task for those students actually who don't have the mathematical background, how actually the results are coming actually. See, in the textbook you can see one equation, they will write the one equation and immediately they will write the second equation, and they actually conclude the second equation based on the first one actually. But you need to understand the mathematics involved in this, right? So this is this value, right? And then you are what you can do, you can put the speed of the light here, okay? And speed of the light I can write 3 into 10 raised to the power 10 centimeter inverse, okay? And nu bar value is generally 10 raised to the power 3 centimeter inverse. It is given actually, right? Centimeter inverse, okay? And this should be divided by the K, which is your Boltzmann constant, and this is what? 1.38 into 10 raised to the power 23, and the unit is like that, meter square kg second inverse Kelvin inverse, and you can write the temperature, room temperature, that is this, okay, this much Kelvin, okay, 300 Kelvin. Now you can very easily cancel the things, right? Meter square will meter square cancel out, this kg cancel out, okay, this Kelvin cancel out, okay, and what we left with this, okay, this is second, this is what, this, and here this is the power 1 actually, right? So you left with the plus 1 only, and this, see, this is centimeter, not see what I made a mistake actually, please wait. Speed of the light is centimeter per second, that means second inverse. So this second will cancel out, centimeter and centimeter will cancel out. So all the units actually you have cancelled. And if you solve this, then it will give you roughly e to the power of negative 4.8, and this is nothing but 0.008. So this is the population ratio, which is very, very important, right? If you are reading the CN bandwidth, then you can find all these things. Okay. Now what we can do, we can actually calculate the energies of the vibration. So now the important task is coming actually, how we can calculate the energy of the different vibrational levels and the energy difference between the vibrational energy levels, energy of the first overtone, energy of the second overtone, all these things we are going to calculate now. So first of all, I am calculating for the fundamental transitions. Okay, fundamental. So how we can calculate this, right? Fundamental transition means your delta epsilon, right, equals to epsilon V equals to 1 minus epsilon V equals to 0, right? Say this is equation A. Okay, this is my important equation. Okay, now what I can do, I can calculate the epsilon 0. Epsilon 0, you know what is the value for the epsilon 0, how we can calculate the epsilon 0. This is something very, very important. This is equals to V plus C. This is V equals to 0, V plus half. That means 0 plus half I can write. This is multiplied with the nu bar minus then 0 plus half square. Now I am including the anharmonicity thing. That's why this square is there. Quadratic equation is there. But sometimes you may need the other order of the equation. Instead of 2, you can write a 3 and 4. But this would be in the different cases, not in our case actually. This is nu bar of xe. Right? This is actually the vibration energy level of the first. This is the vibration energy, right, of the 0th energy level. So this is nothing but half of nu minus 1 by 4 of nu bar xe. Say this is the equation number 1. And similarly you can calculate the epsilon 1. This would give you 1 plus 1 by 2 nu bar minus 1 plus 1 by 2 square nu bar of xe. That will give you 2 1s are 2 to see here. You can do you can use little bit of mathematics. 2 1s are 2, right? 2 1 plus 3, that means it is 3 by 2. So here you can write 3 by 2 of nu bar minus 3 by 2 whole square nu bar of xe, and then you can write 3 by 2 of nu bar minus 9 by 4 of nu bar xe. See, this is the equation number 2, right? There is no problem in that. What I can do in that case, so I can put this equation 1, epsilon c, half of nu bar minus 1 by 4 of nu bar xe, I can put here, and this 3 by 2 of nu bar minus 9 by 4 of nu bar xe I can put here, and then I can take my results. I can derive the result. So what I can write here, from equation A 1 and 2, that means by putting the value of the epsilon 0 and epsilon 1 from the equation 1 and 2 to the equation A. But what we can get here, so here we'll get delta epsilon equals to 3 by 2 of nu bar minus 9 by 4 of nu bar of xe. You can close this bracket, minus half of nu bar minus 1 by 4 of nu bar of xe. You can write like that. And what I can do, I can put the common terms together, right? This is 3 by 2 of nu bar, this is 1 by 2 of nu bar, so I can put these two together, and then 9 by 4 nu bar of xe, 1 by 4 nu bar of xe, I can put these two together to get the final result. Okay, so here you can write like that, 3 by 2 of nu bar minus 1 by 2 of nu bar, bracket close, and here what is this, minus 9 by 4 of nu bar XE plus 1 by 4 of nu bar XE, right? See, when you open this particular bracket, right, so this half would be this plus would become negative, that's why I have put it negative here, and this negative, when you open the bracket, this negative would become positive, so I have written here positive, and this is already a negative, right? So this is your second thing. So what you can do, you can take your new common, and you left with 3 by 2 minus 1 by 2 minus, and here you can take the nu bar XE common, then you will have the 9 by 4 minus 9 by 4 rather, okay, and then, so I have put it a negative there, okay. So what we can do, okay, I can eliminate this negative from here, so I can take nu bar XE common, so this would be your minus 9 by 4 and plus 1 by 4. So what this will give you, see, this is 2 by 2, nu bar of 2 by 2, okay. You can take the LCM, you can take the LCM 2, and then 3 minus 1 is 2, okay, and after that you are having the nu bar of XE, and here you can take, what you can do, you can write this minus 8 by 4, there is no problem in that, you can take the LCM, right, minus 9 plus 1, that will give you the 8, okay, and if you cancel them, this will give you 1, and this is 4 2s are 8, 2 times, and your final result would be like that, delta epsilon equals to nu bar, okay, and then minus 2 nu bar of XE, and then del epsilon equals to nu bar, you can take common, you can write 1 minus 2 of XE. So this is something very, very important. This expression is very, very important, which actually you have written over there, and this is of course in the centimeter inverse, okay. So just like that, it is in centimeter inverse. So what actually result you are getting, you are, see, if you are including the in anharmonicity constant, then for the fundamental vibrations, your delta E equals to nu bar 1 minus of 2 of XE. That means you need to take into account this XE also, and this is in centimeter inverse. I hope this is clear to you. Similarly, on the basis of this, what I can do, we can calculate the overtones also. So here I am going to calculate for the first overtone, my first overtone. Delta epsilon equals to epsilon V equals to 2 minus epsilon V equals to 0, because my transition is happening from the 0 vibrational level to the second vibrational level. That's why that's how I am getting the my first overtone. And epsilon 0 you have already calculated, right? Epsilon 0 you have already calculated. It is nothing but half of nu bar minus 1 by 4 of nu bar of XE, and then you can calculate the epsilon 2. Again, what I can do, I can write this as equation A, this as equation 1, and now you can put, see, 2 plus half, V plus half basically, and we are calculating for the second vibrational quantum number, so instead of V we can write the 2, so 2 plus half, which is the nu bar, minus 2 plus half square of this nu bar of the XE, and if you do that, this will give you the 5 by 2 of nu bar, this will give you minus 5 by 2 nu bar XE, right? This is how you can write actually, okay. So you are having this equation. Now say this is what you can do, or you can see, not 5 by 2, what I did, see, 2 to the 4, 25 by 2, okay. What I can do, I can write it like again. So here you can write 5 by 2 square of this nu bar of XE, and then you will have 5 by 2 of nu bar minus 25 by 4 of nu bar times Xe. Say this is your equation number 2. So now again what you can do, you can put the value of the epsilon 0 and value of the epsilon 2 from equation 1 and 2 to the equation A to get the final result. So I can write here from equation A 1 and 2, del epsilon equals to 5 by 2 of nu bar minus 25 by 4 of nu bar of Xe, bracket close, minus half of nu bar minus 1 by 4 nu bar of Xe. Again I can take the common terms together, so I can write 5 by 2 of nu bar minus half of nu bar. Say this is your first common terms, set of first common terms, okay, and this is 1 by 4 of nu bar Xe, okay, and then you are having minus 25 by 4 nu bar of Xe, right? So here you see, if I open the bracket, then this would, if I open the bracket, this would become plus, so I have written this thing here actually, okay, and this would minus half nu bar, so I have written here, and this is minus 25 by 4 of nu bar Xe, so I have written this here. So if you solve this again, so what you will get, nu bar is common, 5 by 2 minus 1 by 2, and again here you can take the nu bar of Xe common, then you will have 1 by 4 minus 25 by 4, like that, okay. If you take the LCM of this one, then you will get the 4 by 2 here, okay, and then you are having nu bar of Xe. Here you can write, if you take the 4 as LCM, then you can write here 24 with the minus sign, okay. Why minus sign? Because this 25 is greater than 1, okay, that's why I have written here actually. So if you solve this, this will get cancelled 2 times and this will get cancelled 6 times, okay, and final result you will get del epsilon equals to 2 of nu bar minus 6 of nu bar Xe. Del epsilon equals to, you can take the 2 of nu bar common, then it will give you 1 minus 3 of Xe. So this is the energy of the first overtone. This is the energy of the first overtone. So if I arrange these things, right, if I arrange these things, so in the first case you are getting del epsilon equals to nu bar 1 minus 2 of Xe in centimeter inverse, and then for the first overtone you got del E equals to 2 of nu bar 1 minus 3 of Xe in centimeter inverse, okay. And if you want to calculate for the second overtone, okay, then you can do by your own. I am not going to solve this, but you can, see, I can give you the idea in here. So for second overtone, say this is for fundamental vibration, this was for first overtone, and for second overtone you can write del E equals to, so here difference is what, 2 nu and nu, only difference is 1, so another, if you add 1, this will become 3 nu bar, okay, and then it will become 1 minus 4 of Xe centimeter inverse. Similarly, if you keep on doing for third overtone, this will give you 4 of nu bar 1 minus 5 of Xe in centimeter inverse. This is how you can keep doing the, you can solve the various actually relations. So this is something very, very important, right? But this should be, but one thing you should actually note, that the presence of the overtones, basically if the overtones are there, right, this is the overtone, this is the overtone, this is the overtone, if your overtones are there, it indicates the anharmonic character of the vibration, Whenever, if you see, if you are having the IR spectra, and in the IR spectra you are getting the overtones, right? That means your anharmonic character of vibrations are there. And if these overtones or the combination bands, if they are absent, then your harmonic approximation is the best one, right? However, in the pure vibrational spectroscopy, if you are doing the pure vibrational spectroscopy, the transitions basically like V equals to 1, 2, 3, they are not very strong due to the low population and your harmonically forbidden transitions, right? This is something very important. And why the fundamental vibrations are very strongest? Because at room temperature your lowest vibrational level, that is V equals to 0, is actually populated one. And for the hot bands, I already told you the transitions corresponding to the higher vibrational level, like V1, from V1 to V2 to V3, but not from the 0, and this only happens at the higher temperatures, right? That's why the name hot band is given. So here what you can take, you can check one example here. You can check one example here, and this example is very useful. If you have HCl molecule, and for this HCl molecule you get the very sharp band, just like that, very sharp band, high intensity band, not sharp but the high intensity band. It is not so sharp actually. See, later in the series I will also tell you how we can actually recognize the different kinds of the band, which one is strong, which one is weak, which one is sharp, which one is not. See, I'll discuss these things later on, but now you can understand. This will give you the very strong absorption band. This HCl will give you the very strong absorption band at 286 centimeter inverse. Okay, this is basically your fundamental vibration. So I can write FV for this fundamental vibrations. Okay, and then at 5668 centimeter inverse you get the weak band, and this is basically your first overtone. And even weaker even weaker band for HCl molecule you get at 83400 centimeter inverse. Basically this is second overtone. This is your second overtone. Okay, and when actually this happens, right? See, if generally what we say actually, right? Generally we say that your overtones comes from the first overtone comes the double the frequency of or double the vibrational number of your fundamental vibration, and your second overtone comes at the triple of the fundamental vibration. So what you can do here, you can simply multiply your 2886 with 2, right? This is for first overtone, this is for first overtone. So if you multiply this, then you will get 5772. And for second overtone, what you can do, you can multiply your 2886 with the 3, then this will give you the value of 8658. But in reality you can see your second overtone is what? 8347, which is less than 8658 centimeter inverse, and this is also centimeter inverse. Similarly, here you can see your first overtone is at 5668 centimeter inverse, which is actually lower than 5772 centimeter inverse, right? Here you can see it should appear at 5772, the first overtone, but it is appearing at 5668 centimeter inverse. Second overtone should appear at 8658 centimeter inverse, but it is appearing at lower value, 8347 centimeter inverse. This is actually the anharmonic character, right? This, as I already told you in my last slide, actually I told you, whenever you are getting the overtones, it indicates the anharmonic character. That means this spectra is having these vibrations are the anharmonic character. And you know, whenever the anharmonic character is there, you see here, right? For anharmonic character, you can see here, if you increase the vibrational quantum number, the energy gap decreases. That means it is not like your h nu. So of course the value would not be exactly double, but less than the double. It is little less than the double for the first transition, little less than the triple for the second transition due to the anharmonic character. This is something very important. Okay, so this is how you can understand the various things, and you should know actually the anharmonicity constant is of very small magnitude, like roughly 0.01. So you can ignore it. See, why I am telling this, because when, see, for example, nu bar xc, nu bar 1 minus 2 of xc, this is for fundamental vibration, right? And when you ignore this, right, that means you can ignore this, then you can put the value of 0 for this. So nu bar is 1 minus 2 into 0. Okay, that means nu bar. So if you ignore this value, right, then nu bar and nu bar, that means both are same, harmonic or anharmonic, both are same. And similarly you can do for this first, second and the third vibrations also. So guys, this is all about the anharmonic model for the molecules which are having the compression or the stretching of the bond larger than the 10%. You can apply all these things, and this is very helpful in calculating the intensity of the first overtone, vibration energy of the first overtone, second overtone, and so on. Okay, so this is basically the pure vibrational physical spectroscopy of pure vibrational spectroscopy, right? Physical part of that, right? And after that, see, generally pure vibration spectra do not occur. They actually also accompany it with the rotational vibration spectra, where you actually include the BJ part also. But I am not going to explain all these things, because I have explained this in the say microwave spectroscopy. I have explained all these things. So in the next class I will solve all the physical IR spectroscopy problem from the CSIR net examination and some other problems. And after that lecture, that means after the lecture 5, I will continue with the interpretation part, which is very important. So that's it for today. I am leaving now, and before signing out, again the same request: please subscribe the tetrahedral chemistry classes. If you are watching video for the first time, check my channel also. I have made an extensive lecture series for the lecture series on the different topics of the chemistry. You can go there and learn the chemistry from there also. Okay, this would be very helpful for you. So that's it for today. Thank you very much.